Sí, ya. Sí, ya, ajá, sí. Ya, micrófono ya. Perfecto. Okay, thank you very much for staying at the SIMBig 2023. And now I'm very happy and I'm glad to have a good friend of us, Professor Wen Yu. So I will introduce him uh, briefly. Dr. Wen Yu received the bachelor degree in automation from Tsinghua University, Beijing, China in 1990, and the master's and PhD degrees, both in automatic control from Northeastern University, Shenyang, China, in 1992 and 1995, respectively. From 1995 to 1996, he served as a lecturer in the Department of Automatic Control at Northeastern University, Shenyang, China. Since 1996, he has been with Simvestav IPN, National Polytechnic Institute, Mexico City, Mexico, where he is currently a professor with the Department of Control Automático, Automatic Control. From 2002 to 2003, he held research positions with the Instituto Mexicano del Petróleo, Mexican Institute for Oil Management. He was a senior visiting research fellow with Queen's University Belfast at Belfast, UK, from 2006 to 2007, and a visiting associate professor with the University of California, Santa Cruz, from 2009 to 2010. He also holds a visiting professorship at Northeastern University in China from 2006. Dr. Wen Yu serves as associate editor of IEEE Transactions on Cybernetics and Journal of Intelligent and Fuzzy Systems. He is a member of the Mexican Academy of Sciences. So I'm very happy to have Dr. Wen here today. Give us the keynotes, deep learning from or nonlinear system modeling. Okay, thank you. Thank you. Please, I just this go. One. Oh, let me. I need to pull this one. I think this one. Okay, good. Yeah. Okay. So it's the topic. Can start. Yeah. So please. I have 1 hour. You have 1 hour. Okay. So it's a topic about the deep learning for linear systems, and I think most of us is from computer science. So I will try to explain some clearly what's happened for the linear system modeling. But I think that we have some connection. Let's try. Okay, let's see. Maybe I need to connect. Which one? Yeah, okay, right. Good. So it's first one. I want to see where are we. You know, we say it's the deep learning, but for our we call the dynamic system, and here deep learning. We are here, and you can see the field of artificial intelligence. You know, it's here. It's very big. All called AI, and here we call machine learning. Yeah. For us it's machine learning. There are some special case we call the computation intelligence. This is IEEE for engineering. We give it another name. We call the computational intelligence. Not AI, not machine learning. We call this one. So for this one, we call the computational intelligence. This society about 20,000 or more. I don't really know exactly. Maybe 20,000 member. And in this IEEE computational society, we have 3 directions. Neural network, file system, and evolution computing. Only 3. And most people is here. Carlos Valle, you know, he's either chief of the transaction. Many people. This society increase more. And this society state is going down. It's a file system, you know. File system about 30 years ago is very popular in Japan, in China. But now it's a little bit problem is the big problem I think you have knowledge that
gave this system, and they call the fuzzy system or fuzzy logical, and there are a lot of cases. But for mathematics, many mathematics person said this is not a scientific. They said it means you define something, and in this scope you get some result, but your definition is wrong. Okay, anyway, this works well. Yeah, many Japanese people, yeah, you said my wrong, you said my mathematics is wrong, but it was very well. For example, it's many machine, if we call this washing machine, you have the bottom is a fuzzy, it's automatic. Many, it works well. Okay, neural network. So here is deep learning. Yeah, so it's here. So you can see is in fact we say that deep learning is here. Deep learning, the model is neural network. So deep learning, many people I say deep learning, no, it's a learning. Deep learning is a model. This model, the name is neural network. Okay, here, I'm here. I'm also here, and why I put here, because we are in IEEE is computer intelligence, because deep learning is for computer science very, very popular, but it's not in, it's ACM. In computer science, you call the society ACM, but our society is IEEE. So it's a little bit different. So we give another name, we give the computation intelligence. Okay, it means our intelligence based on data, and we use some algorithm. We use computer, so we computation. Okay, so I'm here. Okay, I give you some. My topic is let me return back. My topic is here is deep learning. You know where are we? And now here, I want to explain a little bit about linear system modeling. Linear system modeling. So we said linear system modeling. So we have to start linear. Linear model. Linear model is many cases. Linear model it means the system behavior is a property, and it means is a product and the summary. It's a process. This is very easy, and meaning if you with doubling input and output also doubling. I give some simple property as a linear model. This is many system or many behavior in the nature is linear many, but now we say the nonlinear. What happened? Nonlinear is mean the relation between the variable is nonlinear. It's very complex. Why is it complex? Because physical law is complex. For example, biological is some brain. All of this model cannot be modeled by a linear model. Okay, so we call it nonlinear system. And another case, nonlinear system is dynamic. It should be changed on time. And so in our case, I'm working on controls. We call it feedback. If you have feedback, it's a dynamic. A dynamic should be, we call it change with time. Okay, concoitic, and the dynamic behavior is also needs we need a nonlinear model. And another case, the parameter variation. In our case, we call it adaptive control. It means the parameter system will be changed time. Okay, many nonlinear systems. I can give you nonlinear system with some physiological, neuroscience. They need nonlinear economic financial system. It's nonlinear, and some problems is for the automation problem. We need also nonlinear. Okay, here very important. Here I put here, data-driven system is now we are working here. We call this artificial intelligence. Although this one is so complex, is one case. Another case, we cannot model them. It's not like a motor, like robot. We can give the model, but many research the system we cannot give the exact model. So here we call it data driven. In this case, it's nonlinear because we cannot give the model. We don't know what happened, but we don't know they have some data. So this way is we are working here. We call the data driven system. This system is nonlinear. When we use this nonlinear modeling, I mean, I gave this 3 cases in real world system. They have some complex, dynamic complex. And sometimes we need give we call the exact representation of system behavior. It means it's the sometimes we need analyze some behavior, but this behavior we can not only, for example, you can give the draft, you can give the table. This is one case. This is a model. It's also a model. A table is a model, but in some case we need give some more detailed model. For example, I gave you a differential equation. This is also the model. Differential can be linear, nonlinear. But in many cases, it means why we need modeling. It means we need with exactly very good representation of the behavior. In this case, we call the modeling. This case. And in various cases, engineering practice, for example, for prediction, many cases, it's all of the case we need modeling. So so I give this talk about we call nonlinear system modeling. Okay, let's go continue. Okay, let me give you the example. Very simple example. It's a heating tank. It's a tank, and here the water, and I heat this water. I can give. If I put the water here, the water level will increase. No, it's very easy. I put water here and water level here. So this system is a linear system. It's very special, very typical linear system. This system is first order linear system. We can use ODE as ordinary differential equation. We can describe this one with a differential equation like this one. With the input is water. And output is a water level is here. It can be increased, and if I put some water out, it means water level is affected by the input. Yeah. So this is a dynamic because I put the water here, and the level will increase. So I can use this linear ordinary differential equation ODE to describe this. And this one, in our system, we don't like this one because it's a differential equation. We use an integral. And for control automatic, we use the transfer function. We use Laplace transformation. Sorry, it's Y. It's YS is the infrequent domain. Infrequent domain. There's a differential equation, and here is numerator. Denominator is a linear system. It's very simple like this one. And here is a continuous time. Now is a discrete time. You can see this one is a discrete time. It's K and Ki. K plus 1. And here, all of this one, it means for this very simple case, we can use a linear system to describe. Now, the problem here, if I change the tank from here to here, I can change it like this way. It means the parameter can be changed. The parameter can be changed. So this case from here is linear. Linear is also linear, but only the parameter change. From here to here, we do not need the deep learning. What we need neural network, we can use we call the very famous adaptive control. Very easy. It means I only want to model the parameter here and to change here. Now the problem if I change from this one to here, is that the shape is changed, and I also go out. So this one is non-linear. It means I cannot describe this one with this ODE order differential equation. I cannot describe it. I have to use this one, like this one. It's the input, the word here, is a level now and the level in the next time, and here's the F. Non-linear. It's F dependent, the shape here, shape here. So it's a problem. It's a problem if I want to know the behavior of this one, I have to give this equation. Yeah, I have to give the equation. And if I do not know exactly what happened here, so this F I do not know what we want to do. So we have to we can use a neural network. Neural network is mean if I give the input here, if I can measure that this water level with the input and output, this input and output, I can model this system with neural network. So this is our, we call this one, we call this way is model free. It's why it's model free. We do not need a model. We do not need this one. We do not need a differential equation. We only need data, input and output data. and some knowledge. Some knowledge, it means some shape or something. So this is intelligent model is here. This is it's been how to move from the linear model to non-linear model. If we do not know, I use a neural network. This is the case. It's here. This plan I don't know, so we call this black box. I gave the name black box. This box is black. We do not know nothing. So it's a black box. I have input and output. I use a model. This model name neural network or deep learning. I already say it's deep learning is a neural network. It's special neural network. And I use this input output data. I can use some learning in machine learning. It's here. I use machine learning. I train this neural network such that this one is similar to this one. Or we cannot say this is the exact same, but it's very similar. So we call what this process is modeling. It means I do not know this one. It means I do not need to know this one. I do not need to give the physical model this one, but I only use the data, input and output data. I use some special technique, machine learning, deep learning. I can model this one. Deep neural network, there are a lot of terms. It's universal observation. It means if this plan is continuous, I can use only one hidden layer neural network. I can any continuous plan. There is this neural network can model this one with any accuracy. This is we call the universal observation theory. Okay, like this one. Okay, we call the data-driven or black box modeling with this with a neural network. So only this if this neural network is some special, it's a deep learning. Okay. In nonlinear modeling, we have some. Here I give us some three types. The first type we call the function optimization. Functional optimization is mean in our case we call the mapping. Mapping, what's the meaning? It means we have X input, we call the input of X, some nonlinear function, we do not know F. From X to Y, we call this a nonlinear mapping, no? How to map, for example, sine, cosine, you can make a square wave, the root, any. So from X to Y is a mapping, it's a nonlinear mapping. The problem is I don't know F. I only have X and Y, yeah. I do not know this mapping. But if I know X and Y, I can use a neural network. Yeah, I can use a neural network to modeling. We call the modeling, or we call the identification, this mapping. It means finally I will get a neural network like this one. The X is same, but the output of neural network should be similar to this one. How to do the similar gradient? It's in machine learning. I use some machine learning technique. I can get the model. This one is a neural network. This neural network is the mapping of this nonlinear mapping. Okay, we call the nonlinear functional optimization. It means I use a neural network to optimize this nonlinear function. This is the first one. The second one, time series forecasting. Time series is some special case. Time series is mean I have time series is Y. For example, temperature here is for 1 year. Yeah, temperature today is 20, tomorrow is 21, yesterday is 18. Yeah, the temperature. So it's the time series. This time series we do not have input. Yeah, time series it cannot say it's a nonlinear mapping. Sorry. Time series we cannot write this one because the temperature they have a lot of factors. A lot of factors affect the temperature. So I cannot define some wind, some I don't know, but we have only output. Temperature is only output, only temperature, so we call it time series. Time series only the date, only the output. We do not have input. Okay. The output we call the time series forecasting. It means we can use the history date to forecast to predict future. It means I can use the temperature until now, today, I use this temperature to predict temperature tomorrow. Okay, here is today, yesterday, some 100, 1 year. This is output is a temperature of tomorrow. Okay, here the problem is I don't know. So this is very complex. Yeah, you know, it's climate forecasting is very big area. I remember it's Google just published one model. They say that they can predict the temperature of the world and within 1 week. It's very good. They said it now it's better than the classical measure. So the problem here is we don't know. This is very complex. It means we use the history data to predict future. And now, how to do this? For our deep learning, okay, we use the neural network. We use neural network here. The data, I know this data, I can predict next time, tomorrow temperature here. Yeah, sure, this one, because tomorrow temperature, I don't know this one, but I can use the history data. History about 10 years data, I can use this data to train this neural network, and the neural network can be used to forecast, or we call the predict time series. So it means I use this neural network to model this we call non-linear mapping. But it's a difference with the other one is this is a time series. We do not have input. We do not have, only we have output. Okay, the final is linear system. So linear system for you is a little different because we call it dynamic system. Dynamic system is something like this one. A non-linear system we call the NRMA model. This system, this one, the input has we call the history output is here. I need a YK k plus 1 and the YK k minus 1, and I also need the input. So here we can also see this linear mapping, but the problem is that here the input is one combination of history output and the input. So the only difference. So we call the system. The problem here we have U here. Okay, this is the linear system, and clear now this linear system. I can use the same measure. I can use the neural network to model this one. No, it's no problem. But for our case, they have some problem. After next, I will explain this one. In our linear system modeling, we have we call the two types of model. One type of model we call the prediction model, another is a simulation model. The only difference here is can we use the history output here, or we cannot use history output here? After I will explain this one, but you also know that here we have two types of model. One model we use the real output here. Another one is we cannot use real output. We have to use the output. Here is the output of neural network. It's a neural network, and here there is output real. There's a difference. It's because simulation model. After I will explain this one. Okay. For linear system modeling, as I already said, this is a linear model, linear system, and this is a model. So the difference is we have to give some history output and history input here, and we use some training measure. Okay, I give you an example. I use this example is to show why we use deep learning. Why we use deep as you say, the neural network is about 30 years ago. It's very popular. Many people use the neural network. It works well. Everything is well. But now, 10 years ago, they have deep learning. So why we use deep learning here? No, okay. I use the example to explain why it's okay. This is a gas furnace. Yeah, we use it. We use the heating water now. And the input is gas feed. I give the gas here. And the output is CO2, the output here. And this is a benchmark problem. You can download this the data from the internet. It's about 300 data, only 300. This benchmark is very popular. It's about 20 years ago. many person working on Faraday system, they use this one. Also, they working on this neural network, adaptive control, use this benchmark problem. Benchmark problem, you know now. This means this data is the internet. Data is here. You can use any model as you like, and you use this model, and you should publish your code. You can say your model is better than the other one, no? But the data is the same for the all person in the world. The data is there, and you should also publish your code. You said, okay, my model is better than you. Put your code in the internet, and other person can download your code to try this one. So this means who is better now? This is very interesting. Because this data is not so many. It's 300, not big data, but it's very complex. You can see it's the dynamics is complex, and this one can be use some special technique to model this system. Okay, this system like this one. It means we have input gas feature, gas feed, and we have output CO2, we can go out, and this is because linear system. We don't know that what happened the physical model, we do not know. But in fact, it's a physical process. It should have some physical model, but we don't know. So we can use the Faraday system. We can use neural network to model this one. Here, look, we use neural network to model this one. I give you this one. For example, for neural network, I use this input to the neural network is K. For example, the K is this time and the last time, and the K minus 2. We use 3 history output and 2 input. With this 5 is like input to neural network. I have 5 to neural network, and its output is next time. It's nighttime CO2, okay? The output is nighttime CO2. Okay, it means if I use this structure, I train my neural network. My neural net input is 5, hidden layer 15, the output 1 is the output. Yeah, I use this one very simple, very simple neural network. I use 200 data to train this neural network, 200 data, and then I fix all the weight. The weight cannot be changed after, because the training we can change. We use a gradient method, we change the weight here. And then after 200, after this time, I fix all the weight here. And then I give real data. Because I have from here, I have another 100 data. I put this data to the neural network. Put this data to neural network, I have 100 data. I should have the output. This output is a model, is my neural net. I will compare this output with the real and see what happened is here. So you can see it's very good. Yeah, no problem. It means I can use this 200 data to train a neural network. Its neural network is not complex, and the output is almost similar. It's very similar, very similar. Okay, this is standard. So this is why the 30 years ago many people work on this. Well, it work well for Faraday system, neural network, everything work well. Okay, the problem here, if I change y, because here the problem here I put the input here. Looks, I put the input here. I should be y, no? This y I use real data. It's benchmark real data. But in many cases, if you use a model, you cannot. It is here. It means here I put the y here. No, its y is from here. It means when I run this model, I have to know the real data. I have to put real data to here. But in many cases, it's impossible. For simulation, for example, you cannot get the real data. Or for example, we use this neural net for earthquakes, seismo, the earthquake. The earthquakes mean I want to use the history data, for example, 1 year ago's data to predict the earthquake tomorrow. But yesterday do not have seismo, do not have the earthquake. So I do not have the real data. It means, yeah, because the real data is 1 year, 10 years ago. So I cannot get a real date. The last step is here. It means this date. I have to put, for example, earthquake. I have to put the earthquake of yesterday, and then I can get the next step. No, but this date do not have. So in many cases, I cannot get a real date. I have to use this one. I have to use the date of my model. In this case, this one do not work. Cannot work. If you use a simulation model, I cannot get real date. With this mean I can only use history date, but this one is a neural network, and this one a problem, and it does not work. This means neural network, standard neural network cannot work. So how to work? Deep learning. I use this one. I use a 22 input. It means I put here is just before here is 2. I put 15 more complex, and I put some deep. Just before I have 1 hidden layer. Now I have 3 hidden layers. I use this one, and here I use this structure. This structure is like deep learning. Deep learning, you may see it. Many people say what happened to deep. One is not deep, 2 is deep, 3 is deep, but is many person have different definition. But I think for computer science, you use CNN. I think maybe you have, for example, CNN you need 150 layer. No, CNN is about at least 100 layer. It can work, but in our case we have 3 hidden layers. CNN is very complex, very deep, but in our case we do not use so deep. We have 3 hidden layers. We use this one, and in testing phase, look, we use this the output neural network. It works. Okay, so I give the example. It means when we use deep learning from neural network, I already said neural network it's 20 or 30 years ago, about the first paper published in 1989, 1989, about almost 30 years ago. But now we have deep learning, so it's here. So it means in some complex problem, the classic neural network cannot model so well. So we use this deep learning. Okay, continue. Continue. Okay, we solve this problem, but there are still problems. For example, for this case, I already said it's earthquake forecasting. Earthquake forecasting, we use the similar deep learning model. I already said it's like this one is a time series. In testing phase, if you use this one, and this one is work like this one from K. Here is K plus 1, KK plus 1 work. No problem, it's work. It's work. But from K to K plus 3, it does not work. No, deep learning cannot work. Why? We think the problem is here. It's aftershock. Here is K from K to K plus 1 is like aftershock. It means I have an earthquake here now, and the next earthquake is to be aftershock. It's a replica. Replica is possible. We can predict. But if you want to say I have an earthquake now, how happen next year? They have an earthquake or no earthquake? Sure, you cannot. Nobody cannot. So it's like this one. We cannot. It's a problem is here. It's a problem is we cannot use a deep learning or neural network to model the mechanism of the earthquake. It's impossible. In fact, everybody knows we cannot predict earthquake. Yeah, but why we cannot predict earthquake? It means any neural network or any deep learning in general, it cannot do this one because it is so complex. It's like things. For example, you want to predict people the cambio in that we call the exchange rate is Mexican peso and the US dollar. Nobody can predict. Why? Because there are so many factors. Yeah, there are many factors. It's because the price, oil price, the Biden say something, There are some here in Iraq, in Ukraine, in Israel. All of these affect this factor will affect. So this system, we call this system is so complex. So it means deep learning can solve some problem, but it's some very complex problem is some difficult. But our research is like we want to try is, I mean, if this one cannot do so well, maybe we can change what we call the modify the deep learning technique. For example, STM, CNN. After I will show you some special modification for special case. Here is we have a very famous theorem we call the free lunch theorem. I think all of you should know this one. This free lunch theorem is mean in the world it do not exist unique algorithm or unique method to solve or to say you have a unique method. It is better for any data set. It's impossible. We can only say like this one. For data set A, there exists optimal method A. For data set B, you can say, okay, you can design an optimal method for data set B. But for both data set A and B, you cannot design optimal method for both of them. It's impossible. We call it free lunch. It means in the world, they do not exist free lunch. You can only design special algorithm, we call special deep learning method for special data. We can only say this one. Okay, this is our object. So in the future, I think some students also like this one. It means you can design your method, but your method only solve this special case. It's okay. That's all. You cannot say my method can solve all of this general problem. No, it's impossible. We call the free lunch. There do not exist free lunch. Okay, here I'm continue. So all the method I will discuss in the future is mean we design some special techniques of deep learning for special case, special data set. Here I gave the three methods and we call the four base because transfer learning is not a model. But the first three model is very famous deep learning. Retrieval machine is the first deep learning model proposed at Hinton. Hinton is the father of deep learning in Canada. But retrieval machine now nobody work on this one. Because I don't know, maybe you know why nobody work on this one. It's so complex, very difficult to do simulation, to calculate, to analyze, because they manage probability. Okay, but Boltzmann machine is very good. I mean, Boltzmann, no? Boltzmann is from we call the it's from dynamic is the movement rhythm. Boltzmann is that the Boltzmann constant is to calculate the temperature. But so Boltzmann machine is it's like a rhythm work, but it's very good for deep learning. But now nobody work on it. Almost nobody. CNN is a convolutional neural network. It's for all of imagine precise you see it. And if you said I want to do some imagine video, if you do not use CNN, if you do not convolution, you said you're so stupid, no? All of imagine video have to use convolution CNN. You should know this. STM is recurrent. If your problem is recurrent, like a language you have relation, like I am a student, no? You cannot say I was no, you can I are student, no, I must be connected with M. So this is we call a recurrent, some relation. It means if you have some relation with before, you have used STMs. Now it's about ChatGPT, no. STM can deal with about 10. The sentence with 10, but ChatGPT with the transformer, it can use, now they say have I remember it's 5,000. You can get a relation between now of 5,000 of people. It means ChatGPT can deal with one article with 5,000, but STM can deal with one sentence about 10 or 20. So there's a difference, but similar. ChatGPT uses the similar model as STM, but this is another STM. It's a second generation STM. They call it transformer and attention. I think some work. I large language model. But similar like this one. So it means these two deep learning model. One is for emerging, as this one is for recurrent, very popular. And central learning is only measured. I will explain this one. Very quickly. I give some idea because mathematics is so complex. I can only give some idea. It means how to use this reinforcement machine for linear system modeling. This is a reinforcement machine. For the reinforcement machine is like your neural network is moved from this part to this part. All of neural network like this one, for example. Like I move how to go. The data from here go this way, no? It's a neural net. But reinforcement machine to go this one, I return back like this one. Move like this way. Until to go some equivalent point, some balance point. This way, this means from here to here to go there and go back like this one. Move. This we call Markov sampling. Markov sampling is random sampling, and this reinforcement machine is the first use is in we call the unsupervised learning. I think you should know Hindun in 1921. I forgot it. He published a paper in Science. And somebody asked him, what's the difference between deep learning and the neural network? He said it's something interesting. He said the big difference, there are a lot of difference. He said one big difference, the unsupervised learning. He said we are in the big data time. If we all use the supervised learning, we need a label, no? Label is supervised. But so many data, we need unsupervised learning. It said if we can run unsupervised learning very well, he said if we have a very good mechanics to run unsupervised learning, this can help us a lot. It can improve neural network. So he said that unsupervised learning is a very big advantage of deep learning. It means because we use unsupervised learning, so the neural network, the property of neural net can improve a lot. So in this case, neural network is said deep learning. He said, but there are a lot of. I think for my opinion, deep learning, the big jump of deep learning is feature extraction. Yeah, for my opinion, the feature extraction, CNN, the feature extraction. It means we use some technique, we can obtain the feature, some convolution. Like this is we call the Boltzmann machine. It means we get some feature, some special technique that get some feature. So Boltzmann machine is in fact is unsupervised learning. Why is unsupervised? Because it moves like this one. They do not need label. And finally, to the equivalent point, the feature is here. He said the feature is here. The weight of this one is feature. So it's how to do this one. We use unsupervised learning first one, and we get some good feature, and we move the feature to the neural network. Because if we do not do this one, we start from here. Neural network, is a local minima, no? It means you start from some bad initial condition, you will stay in local minima. It means your gradient cannot move further, because if you arrive local minimum, your gradient is 0. If your gradient is 0, you cannot move. Your weight to be stay here. but it's not good. It's not a minimum. It's a local minimum. Why? Because your initial condition is good. But how to avoid this problem? He said, okay, we use unsupervised learning to avoid this. And Hinton also used this one. He gave the name is pre-training. A pre-training is here. It means he uses this one pre-training. Before your training, he got some feature here, and he gave the name pre-training. Another one, he called it the fine training. He had 2 steps. Unsupervised, supervised. This is the idea. And we use this idea, Hinton's idea, and we use, because Hinton use this one for imagine, classification of imagine, but we use this one for system. It's similar. Like this. For the system, we use supervised, unsupervised, supervised. And we also use this idea for the fuzzy system. And I don't give the idea. Fuzzy system, in fuzzy system, we have one big hyperparameter. In fuzzy system, it means how many rules we need. Yeah. When you design fuzzy, you need to design how many rules. And this hyperparameter, we can use the Boltzmann machine to guide. And this is running with Boltzmann machine is we call the custom cascade one by one to go. But this one important, very important is Boltzmann machine. You can see here is unsupervised. We do not have a label. It means we have only input. It means we change the weight. We change the way to learn input. We do not have output. We do not label. We only move, go here, move, go here, like this one. This is the Boltzmann machine. Okay, it's the second one. Second one is CNN. CNN is very, very popular. So most people, you know this one, classification. And I have imagine here. No, I use convolution. It's a standard CNN. And we use this idea to modeling. We call here the classification, although you use the classification for imagine and regression. We use regression also for CNN. So only different here and here you use imagine here. Because I have time series, I have date here. So I have to put date, for example, here I have to put data for 1 dimension or 2 dimension. 2 dimension is like figure, no? But I can put the velocity here, I can put the acceleration here, and this state here is like imagine. Yeah, it means we have to transform the data set to imagine. Why? Because CNN is deal with imagine. I have to use this one. So you can see it's a similar like this, but here is imagine and here is a date. It means we further we do this transformation and we get this like here like imagine, but in fact it's a date. And we use the similar way. This we have some special modification for CNN, but in general structure is similar. Now we change from imagine to date. Okay, and here the application of CNN, application of CNN we call the structure character monitoring. It means, for example, for this bridge, in the United States, many bridges now they install here. They put this we call the accelerometer. Accelerometer can measure the vibration of this bridge. It means if the vibration was this bridge, for example, there are some many sensors here, and there's Wi-Fi to send to all of this vibration data to computer, and they will monitor the vibration, the bridge. And if some happen, if there are some damage here, and this vibration we call the natural frequency to be changed. If they change, it says, okay, here, for example, this sensor has some uncertain, abnormal vibration. It means maybe there are some damage here. It means like this way, we call the structure chaos monitoring. Okay, now they are doing like this one. Okay, what do we want to do? We want to do classification. Here, it means they only monitor the vibration, and it's to say if the vibration is abnormal or is good and no. But in fact, there are so many noise, there's many the track is many uncertainty. So the vibration here will be changed a lot. So how to do it better? Better is we call the classification. Its classification means if we see the natural frequency always change. We had better use PCA like this one. We call it classification. Classification is mean if the vibration inside here, we can say, okay, it's abnormal. If the vibration the outside here is normal, and here we only need to find, we call the classification border, this one. So how to do that, as you know, SIMBig machine, neural network, all of it can do classification. No? It's classification. What we want to do is we want to use the normal data and the damaged data. With these two data, we can train, we can get this border, no? This classification. Okay, now the problem. The problem here, we do not have this data. We do not have damaged data. Yeah. Because if the damage, the bridge is collapsed. So this data we do not have. We have only this data. We have only good data. We do not have bad data. Because the damage, the structure is bad. So we do not have. So in this case, in civil engineering, in fact, they do this one. They artificial generate this one. Because they do not have real. This bridge, all of data here is good. It means the bridge is healthy. It's good. But the bridge is unhealthy. There are some damage, the bridge collapsed. So we do not have damage data. Okay. They do this one. They generate damage data and they can measure the good data, and then they use some neural network to classify this one. Okay, this is not so good. So you see. And for us, we want to do, we do regression. You can see this. For CNN, we have two choices. We have two options. CNN is a classification. Classification needs good data and bad data. Then we get this border. But for regression, we do not need bad data. We only need model. We have data, we can give the model, as I said before. I have data, I have input, I have vibration data, I can give the model. It means I can use the data of this bridge. I can use the vibration of this bridge. I can give the model of this bridge. Okay, if like this one, if the model is changed, it means the bridge is damaged. So it means in computer science, we said classification and regression. We do regression. So we do regression, we do not need the bad data. We do not need data. It means I use all of the data of outside, I can get this linear. It's a regression, it's a modeling. I do not need the data. Okay, this is a good, it's an advantage application. So we use in our laboratory, we do this one. We use this accelerometer is to here to change to measure the vibration, and we do like this one. It means in laboratory we do is the normal I modeling, and I gave the model is a good model of this one. If I change this model, I can use neural network. I give another model. It's a good model, a bad model, and then I can check what happened. The vibration you can see when I gave the model, when I gave the vibration to pass a good model and pass a bad model, I can see the difference. And for this difference, I can see what happened, the damage. Okay. This is here. The next one is the STM. I give very quickly. Is for it's a project with Italian, and we use the earthquakes in Mexico City, and Italian we use the time series of the earthquake, and we use STM to give the model of the earthquake, and we use some special. I think there's a bifurcation to I go this very quickly. It means we can use the STM to model the earthquakes. I mean, it's like a replica. We cannot predict the real earthquake, but we can predict the replica. We call aftershock. And here is a bifurcation, is some special modification. Okay, I go very quickly. The final one, we gave this application with a transfer learning. We call it meta transfer learning. Here's air pollution in Mexico City. And so is there some points that to measure this index of air pollution? The problem here is means most of the point they cannot give the complete state. Sometimes they do not have rules. That some person do not get the value here. So in this case, for example, is for this point 26. In this point is Gustavo Madero, for example. They use some date from academic for some station near from here, and it means if I lost some date here, I use the date near from here. It means I transfer the data from here to here. It means it's all of in scientific we call the missing date. It means I have missing date here. I have to transfer from here. Okay, this idea is very normal, no? It's very normal. But for deep learning, it's another one. It means how to transfer them. There are several ways. We do this like the first one. We do like combination. It means we can model this one. And we use it to model to improve this model. This is the first one. It means we do not move this data here, because when you move the data is not so reasonable. It means if, for example, I lost the data is yesterday at 2 o'clock in the afternoon, but I cannot use this data at 2 o'clock because this data is also not so good. We want to use the group data. The group data here to here, a group data here to here. Not one data. If you one point to here, it's not improved so good. So it means we can give the model here, and the model these three model. Then we combine these three model. It means we use these two model to help this model. How to do this one? We combine these three model. This each one is we call the ARIMA model, and we can use the neural network to combine together. Is the technique here we call a multiple model. Or we can use one model and use another model to improve that we call comparison. Is the first one we call combination. Is we combine all together, the three together. Another one we call the combination. If we use two combine to improve my result. Okay, that's all. So finally I gave some common the future of this our work. Neural network, something like 1970, something is popular because after that we have big problem. We call SOR problem. It means we cannot solve the problem by we do not have backpropagation. Backpropagation come here is it says no. It's hidden three groups in MIT. They gave the backpropagation and they solve the problem. It's very popular. In 1980, about 30 years, a very popular neural network. And after that died. In 2012, 2010, 2012, I have deep learning. And the neural network, again, a lot of people start to use neural network. And the big data, something is very popular. After that, I think last year, we come to ChatGPT. So I gave the conclusion that like here, the future of the artificial intelligence is our intelligent model. This is my idea. It means we use all of recent good technique in artificial intelligence. We use their techniques to solve our problem. For my case, I work on automatic control. So our problem is low linear system modeling, navigation, automatic control. It means their future is my future. It's our future. We have to follow them like this way. Like there's a neural network, backpropagation, deep learning, ChatGPT. We have to follow this way because all of this is artificial intelligence. It's there, the computer science. Okay, this is my talk.
If there is any question, please
No.
let us know.
Or some comment.
Or comment.
Since these nonlinear models and nonlinear systems are very complex, and I think you show an example of transfer learning.
Mhm.
but can we, with deep learning, have a model and then you do the transfer learning in another complex dynamic model? I'm not dynamic, non-linear model.
You mean it's for the model now we use transfer learning. For transfer learning, for my opinion, they have two cases. Transfer learning, you can transfer date. The other one to here is transfer, we call the date. Or you can transfer the model, their model to here. As you said, it means, can we transfer the model to here, no? Yeah, this is it. For our opinion, transfer model is better than transfer date because your transfer date you can transfer 3 date now, but the transfer model is mean we give a model 1 million date, give this model, and then we transfer this model to here. It means 1 million model date can be here, not only 3 date. 3 date is some outlier, some disturbance is not so good. So for you can see many people now in transfer learning, they do not transfer date. In fact, they transfer model. It means you have model, I have model. No, now we combine our 3 models here. In fact, it's like this way. In fact, I use model A, but how to use the data of here? I do not transfer this data to here. In fact, I give the model. I combine their model here. It's similar. I have model. I do not transfer this data here. Sure, you can put these 3 data together now. You have and then give the model. It's not so good. Okay.
Thank you. Is there another question? Yeah, please.
Thanks. In a lot of your slides, you're always showing the ARIMA model. So in your experience, do you use the ARIMA still in the hybrid version? Like, is it performing best in your experience for most of problems?
You mean the ARIMA?
The ARIMA, yeah.
Yeah, it's
in the hybrid with some network.
Yeah, it's I think it's many paper on this one. It means time series forecasting. For my opinion, time series forecasting, the best model is ARIMA.
Still from the statistics.
Yeah, it's very. Is we call the outcome theory. I forgot the name. It means if you can use simple model to do something, you had better do not use complex model. It means you can use simple model to solve this problem. You should better do not use complex model. This is a general case. It means for time series, ARIMA model is linear model. It's very simple. If it works well, go ahead, use this one. You had better do not use neural network. Okay, neural network can also, sure, it's black box can also, but the accuracy almost the same. Okay, in this case, we use simple mode. We do not use complex mode. So here I have it. So the idea is here we can use a simple model to solve this problem. Okay, we use ARIMA.
Okay, so there's this stream with all this transformer-based architectures also for time series forecasting, but you say, okay, if this works better.
Yeah, it's better.
Hybrid or
sure, it's better. Yeah. For our simulation, I saw a lot of paper. Not only is, for example, air pollution, temperature, even financial data. ARIMA work well. It's work. ARIMA is work.
Okay, also for like long time.
Long time is done. Okay, long time is not so good, but ARIMA is also good. I mean, for time series. Time series.
Thanks.
Yes. Someone else?
Yeah, good.
Can you use this for computer torque control? Computer torque control?
Storage. Computers, what?
Par or torque? Torque?
For
example, linearization, exact linearization. I don't know how do you say, pero yes, this It's like model the dynamical system and use this model for feed forward. I think it's computed torque control. But
okay. I got it. The computed torque is the force, no? Computational force. You calculate the control force. Torque, not control force. Yeah.
Yes.
But it use model. You need the model. Yeah. This is yeah. I have worked on. In this case, we call model-based control. No, model-based control.
Okay.
Model-based control, it means you need a model. Yeah.
Yes.
Okay. If you do not have model, you have only data. How to do model-based control? Neural network.
Okay.
You understand? You have data. I do not have model, but my control need a model.
Yes.
How to do this one? I use this data. I gave them a model of this data. What is the model? It's a neural network. And then I design my model-based control based on my neural network. Because my neural network is a model. Maybe this model is not different with your model because your model is a mathematical model with differential equation. No?
Yes.
But my model is neural network. It's also possible. It's also possible. There are a lot of work on about, for example, feedback linearization. Feedback linearization need a model, but we do not have model. We only have data. So how to do feedback linearization? We first gave the model of this one, but the model of this one, the name is neural network. Okay. Then I use the neural network. This neural network is a model. I can design my control. I can design my model-based control. It's like this one. It's first we have to get the model. This model is this one, neural network.
Okay. Thank you.
One more question. Yes.
Yes, you are dealing with linear model. So we have on one side linear model and the rest. But on non-linear model, they are not necessarily of the same complexity. For instance, quadratic or cubic models like this are more easy to handle. In your case, do you consider that all non-linear model has the same level of complexity?
Yeah, you're same structure. You're right. Same structure. Because the structure neural network the same. So it's this is problem because the hyperparameter of this model. The hyperparameter of the model is now it's always the problem is our case. Because now you I think you know that we call it explanation artificial intelligence explanation. How to explain this one? This is a black box. We cannot explain. As you said, it's the same. All of nonlinear system, I can use the same model. It's not explainable. I cannot. So this is a future work. It's a future work. Now we cannot do this one. You're right. All of nonlinear system, I can use one model to do all of you. Like this. It's not explainable. It's not reasonable. No, you say not like physical model. Robot is model one, and it's the moving car is another model. We can see the differential equation different, but my neural network is same. For your two cases, same.
Okay, thank you.
Thank you. More questions? Well, I have a question, Professor Wen. When you have this unsupervised model, how can you be sure that you are getting the best model? Because as data can be arranged or subdivided in many different ways, like for example, in the graph you put that creates like kind of a head or something.
You're right. It's right. It's a problem. So Hinton gave the name here. It's pre-training.
Okay.
It's pre. So this result is nobody know.
Not ready to be used.
No, not ready. Not ready. It's a pre. It's like a pre-processing. When your data you have to pre-process it, but no start to work. Still to not so it's pre-speed. Yeah, we cannot do this one. Only pre-train and after they start to train.
Good. Nice. Thank you. Well, if there are no more questions, Okay, then we thank Professor Wen for his magnificent talk. And now I think we have one last talk. So please come here. Have you loaded your presentation? Yes. Okay.
En el escritorio, en una carpeta.
SIMBig. ¿Tres SIMBig?
Sí.
¿Estás?
Sí.
Okay. Perfecto, nos vemos con este, y aquí tienes el enlace en esta carrera.
Gracias.
Exactamente, para iniciar.